will see this and close. Right? This is to let you understand the laminar and turbulent flow. I am sure you might have studied this in your fluid mechanics, isn't it? So you very well know. So laminar flow is very smooth and orderly. Like one layer, it's like people moving in a queue can be considered as an example for laminar. And the people who broke all the rules and they are not standing in queues and everybody is trying to gather at the window where they should take something. That is like turbulence, right? To put it very roughly. But see, the layers, they are moving in one particular direction very smoothly, one layer over the other. See, this smooth transition is happening, smooth motion is happening up to a particular point. And thereafter you see, the circular motion is created. Just imagine, I gave this example earlier also. Water is flowing smoothly in a canal, and you are throwing a stone into it. So that effect is to break that rhythm and create disturbance in it. So what is the impact of this? Technically is the molecules of the flowing fluid are moving in the perpendicular direction now, right? From top to bottom or bottom to top. The motion is created, the circular motion is created, and the perpendicular motion is created. Still, there are some layers which are following the laminar path because the effect of this surface is more there, right? It is not allowing it to go up because the forces that are holding it are still higher. So therefore, you can find one or two layers. That's why it is called viscous sublayer, right? So then, beyond a point, even this may also be getting affected. So here, this is turbulent flow, here it is laminar. What is the effect of that on boundary layer? If you see here, the velocity here, if you see velocity gradient, it is continuously increasing till this point. Whereas you see here, it rapidly increased up to one point and thereafter it is more or less constant. So the effect is not extended up to this point. The reason is very simple. In this case, every layer is moving in its own path. Therefore, it is following a pattern. One layer above is slightly at higher speed compared to the lower layer below it, and it's gradual increase. Whereas here, what is happening? The top layer is getting down and the bottom layer is getting up. So therefore, that mixing process is not allowing the layer to go in its own direction. Right now, everything is mixed up. See, we do this. No, see, whenever we want to say mix, say milk and water, or buttermilk and water, or curd and water, right? We thoroughly agitate it. We thoroughly mix it, so that you don't see water and buttermilk separately. If you let it alone, water floats on the top, and then the denser particles will go down. But the moment you rinse it thoroughly, right, you agitate it, then you can't find any difference between them. Here also you can't find any difference between layer and another layer. So therefore, very quickly, right, all the molecules or all the particles will acquire the same velocity. Are you following me? So the effect is neutralized. Fast moving particle and slow moving particle, they are all mixed up and they came to some average speed. Because you are not allowing fast moving particle to go on its own, and it is affected by so many other things. See, it is now again you can relate it to so many different practical cases. In this class, right, there may be some advanced learners, there may be some slow learners. But now, because we don't have any mechanisms where we can teach this set and that set of students separately, if anybody obviously is going through an average space, right? Suppose if it is done and all advanced learners are put in one class and others in another class, I would have completed 4 units by now. Because they are quick learners, I need not spend this much time, right? But now here it is mixed up. Therefore, all the students are moving at the same pace. So that is the meaning of this turbulence. So just make a note of these 2 points and then we can close with reference to this figure. Now, this is a dimensionless parameter, Reynolds number, which is used to determine at which point laminar flow becomes turbulent flow, right? So it includes the parameters like the density, velocity, resistance, and then viscosity. So based on these properties, it is a dimensionless group which consists of these four. And for a given condition means these are all affected by the conditions. And then for a typical geometry, say if it is a flat plate, it is 5 into 10 power 5. If the Reynolds number is more than that, then it will become turbulent. Before that it is laminar. Of course, for some period there is a transition which is neither pure laminar nor pure turbulent. That's why we have shown a small region where it is transition. So therefore the significance of Reynolds number is it is used to find out where the laminar flow is changing into turbulent flow.